Okay, so for quiz, ask everybody to sketch a graph representing the rational function. That's all right there. R of x plus 2 times x squared plus 3x plus 7 over x squared plus 5x plus 6. Now, the thing that surprised me a little bit is that most of the group didn't seem to understand how to solve a quadratic equation. Okay, as soon as I said that's a quadratic equation, everybody started using the quadratic formula. So you knew how to solve it, you just didn't recognize that you had it. Okay. So the other thing is, I'm not saying the kind of logical development of the problem that I think would most benefit you, because it reinforces all the details. I think there's a better R there. Okay, so let's start with setting the numerator equal to 0. That means that x plus 2 times x squared plus 3x plus 7 should equal 0. And the only way that's going to equal 0 is if this equals 0 or this equals 0. Now, I urge you to write this out. This means that x minus 2, x plus 2 equals 0, or x squared plus 3x plus 7 equals 0. Not and, it's or, because it can't be both. If x minus 2 is 0, this isn't 0. So if this is 0, though, or if this is 0, you're going to get numerator equal to 0. Well, this has solution. X equals -2. And you add 2 to both sides, you get x equals -2. Or x equals -3 plus or minus the square root of 3 squared minus 4 times 1 times 7 divided by 2 times 1. Just plug in the A, B, and C in the general form of the quadratic into the quadratic formula. Well, then this gives us -3 plus or minus the square root of, that's going to be -28, that's 9, that's -19. Okay, well, if we're at a -19, we can find that square root over the complex numbers, or the imaginary numbers in this case, and there we have it. But that's not a real number. It doesn't give us an x-intercept. So this is not real. X-intercept is at -2, 0, provided that x minus 2 is not a factor of the denominator. That's going to turn out that x minus 2 is a factor of the denominator. Okay. The denominator. X squared plus 5x plus 6 equals 0. Now, you might or might not notice that that's easy to factor. You might or might not factor it. So I say, that the solutions are x equals -5 plus or minus the square root of 5 squared minus 4 times 1 times 6 divided by 2. That turns out to be -5 plus or minus 1 divided by 2. And that equals -4 or -2. And I can't add -3 or -2. Okay. And I'll also note that if you factor it, this is a factored form, and you easily get solutions from the factored form. Well, now I said that this would be a 0 provided x minus 2 isn't a factor, or x plus 2, sorry. X plus 2 isn't a factor of the denominator. It turns out that x plus 2 is a factor of the denominator. That'd be completely factored. R of x would be x plus 2 times x I still didn't leave myself room, sorry. I'll write it. Make sure I have room. I'm going to start over here. Okay, it's going to be x minus this 0. Yeah, one of the two zeros here, x minus the other 0. Then you got x minus 2. Now I write this out because we've done complex zeros, I think, and you've probably seen them in pre-calculus. So this is the completely factored form. Now these, there's an I, there's an I. Okay. As far as graphing the function, you don't need these. Okay. So as far as graphing the function, you could just say that once you found that you don't get real zeros from this quadratic, then you call that an irreducible quadratic. Okay. But then it's divided by x minus 2, x plus 2 times x plus 3. and this is x plus 2. Okay, and you see that you can divide the x plus 2 into the x plus 2. Now, before you do that, you say if x is not equal to -2, r of x equals just this mess. Divided by x plus 3. Now, as I say, when you're graphing one of these things, you usually don't bother. Once you get to the point here where you see that this is not real, you know that there are no zeros. Okay? If this is multiplied out, and if I did this correctly, its numerator is just x squared plus 3x plus 7. The denominator is x plus 3. And the numerator is irreducible. And we could have just said that originally. We could just put that here, noted that it's irreducible, and we could have gone on. Now, x as if x is not equal to -2. Why can't we do this division if x equals -2? Because division by 0 is undefined. And divide by this, because you can't divide this, because you can't divide by 0. Obviously, you can divide by negative. Okay, so x equals 2, this is 0, and this is 0, and you can't divide 0 into anything, not even 0. So x minus 2 is what we call a whole. In the domain. There's no point for x equals 2, because 2 isn't in the domain, and eventually I'll get my negative signs right. Okay, x equals -2 is a whole in the domain. All right. So what else do we have to check? Well, the y-intercept is 0, r of 0. And r of 0 is Okay, well, it's this, we just replace all the x's by zeros. That's just gonna leave us 2 times 7 over 6, which is 14 over 6, or 7/3. And one more thing. The degree of the numerator is 3, the degree of the denominator is 2. When the degree of the numerator is 1 more than the degree of the denominator, you do a long division. Okay? So do a long division. And when you do the long division, well, before you can do the long division, you have to expand the numerator and expand the denominator. In this case, we have to expand the numerator. What's this equal? Well, I want to emphasize the distributive law once more because I find that people are sometimes still shaky about it. I have a whole lot of room. It says that x plus 2 times this is x times this plus 2 times this. And what you get then, you're going to get an x cubed. I've done this before. You know, you multiply these, then you collect your terms. You're going to have a 3x squared here and a 2x squared here, which gives you 5x squared. You're going to have x times 7 here, which is 7x, and 2 times 3x, which is 3x. That's going to give you 10x. Then it's going to be plus 7. So now we can divide x plus 2 into or we divide the denominator, which is x squared plus 5x plus 6 into x cubed plus 5x squared plus 10x plus 7. That's pretty easy. Get x here, get x cubed plus 5x squared. And remind ourselves that these will be subtractions. That leaves us 0. And that leaves us then 10x plus 7. Of course, we can divide x squared into 10x. So we have x plus 10x plus 7 divided by x squared plus 5x plus 6. When x gets big, this goes to 0. Now the horizontal asymptote, writing words down without thinking. We call it slant asymptote. At y equals x. It would have a 0 at x equals -2, except -2 is not in the domain. So -2 is a hole in the domain, so you don't get a 0. So our graph now has y-intercept at 0, 7/3 here. The x plus 3 in the denominator gives us a vertical asymptote. And x equals -3. Its long run behavior is just y equals x. Here's the line y equals x. It should have gone through the origin. I just missed it. But you understand? It's like this. Okay, this means that the graph starts out with really big negative values. Sorry. Yeah. Really big negative values. Comes down to this. If x is a huge negative number, this is positive, this is negative. It's got to come along the x equals 3 line. It's got to have a vertical asymptote here, which means I did a lot of writing right where I need to draw my graph. But it's going to come up like this. And it's got to turn around and approach this vertical asymptote. Over here, it's got to come down the other side of the vertical asymptote, so it can go through this and come up and be asymptotic. I just moved away from my asymptote. You gotta move closer. Asymptotic to a y equals x line, and there's a picture. And get the picture on the board again. We have the y-intercept at 0, negative. It's 0. Whoa. I'm just writing all kinds of negative signs when they go below. I said -7/3 there, but obviously I got 7/3. I didn't get any negatives here. Okay, So I graphed it correctly. I wrote it down there wrong. Okay, so it's a good thing I didn't try to follow that, because then I'd have had to come down from here and go through the zero down here without going through the x-axis, because this thing doesn't have any x-intercepts. It would have had an x-intercept at x equals 2, -2, but we had to divide that out because of the x plus 2 factor in the denominator. Okay, so that's about as complicated as these things get. If we go back and look what we did, we started by finding the zeros of the numerator and the denominator. Over here. Okay. We found, and that's the first thing you want to do. And incidentally, we want to write out our solution to numerator equals 0 like this with the or, and emphasize that we understand the zero property of multiplication and how it applies here. Otherwise, if you're not used to writing this out and you get on a test and have to do it, you might not remember as well. If you keep writing it out with all the logic, you are going to be much more likely to remember what to do. What I typically see on tests where people haven't been doing that is I see a bunch of calculations scattered on the page with no coherence. Okay. And they never get to the right answer because they lose track of what they're doing. They forget, I do this, now I do this, now I do that. Why do I do that? You don't know. Okay. You want to know why you do things. Otherwise, as I say, much less likely to get everything right. All right, so there it is. Structure your solutions. That's my main point here. And this is a good example of how you can structure your solution. Logically, find the zeros of the numerator, find the zeros of the denominator. You put the thing into its completely factored form. When you do that, if you hadn't noticed that there's a zero of the denominator that matches a zero of the numerator, you're going to discover it when you do the completely factored form. You're going to have an x plus 2 here and an x plus 2 here. I incidentally included the complex zeros because that's a current topic or an upcoming topic. Okay. And sometime you might have to do that. If your task was to graph a function, you didn't need to actually write out the complex zeros. Once you found that the zeros were complex, you knew they weren't going to contribute x-intercepts. They do have their effect, but we're not going to go that deep into the topic. Okay, now, then you write out. You can't divide x plus 2 into x plus 2 if x is equal to -2. Okay, because that's what you're doing. You don't just cross things out and start canceling. You're dividing this into this, and you can't divide by a 0. And that's what you have, x equals -2. So you say if x is not equal to -2, you get this. And again, this could have been left in the form x squared plus 3x plus 7 with a note that it's irreducible over the real numbers. Then explain why you can't divide. Then we find the y-intercept. And then we note that the degree of the numerator is 1 more than the degree of the denominator. In that case, we've got a slight asymptote, so we do a long division. We do the long division, we find out what the slight asymptote is, and we throw it into the graph. There's my slight asymptote. Again, I missed the origin. Pretend we got a big fat origin there. Here's our long division that justifies this. If a long division tells you that this is the denominator divided into the numerator, and incidentally, we did have to expand the numerator so that we could do the long division. Okay. The quotient is this, which means that this equals this times this. In any case, there's your divided form of this function. This term, when x gets big, x squared is way more powerful than x, drives everything to zero. There's your asymptote. Here's the asymptote. Here are your long run segments of the graph are going to be asymptotic to line y equals x. We've only got one point to go through because there are no zeros. Okay, well, there it is. Again, start out with the logic. Numerator equals 0, denominator equals 0. Find the y-intercept that happens when x equals 0. Okay, and then go from there. That's where you got to start. Then little twists can come along, like here, where you have a factor of the denominator that equals a factor of the numerator. You got to deal with that. Okay. Okay, that's all I'm going to say about rational functions. Unless somebody wants more. Okay. And we can always do that. Okay, you know, of course, it's really built on toolkit functions, which is a little mystifying. It's a little mystifying that by the end of the course, nobody knows what the toolkit functions are. Okay, you want to keep going back and seeing how the toolkit functions relate to everything that's being done. Okay, well, you have this y equals 2 to the x toolkit function. Now, if you're in my class, you're very familiar with this function. But if you're not, let me just graph it by making a table. Matter of fact, I'm going to give you a minute. Fill in this table and do it this way. You have a third column over here. Which shows a calculation of the exponential function. For example, when x equals 2, y equals 2 squared, which is 4, right? So you're going to put a 4 here. Well, do the same for all these other values and see what you get. Give you a couple of minutes to do that. And even if you're in my class, do that, write it out. It's always good to reinforce what you already know. X equals -2. You get y equals 2 to the -2. What's 2 to the -2? It's 1 over 2 squared, which is 1/4. For x equals -1, you get y equals 2 to the -1, which is 1 over 2 to the 1, which is 1/2. If y equals 0, x equals 0, you get y equals 2 to the 0, and any number to the 0 power is 1. X equals 1, you get y equals 2 to the 1, which is just 2. Now, if we look at this series of numbers, 2 is half of 4, isn't it? And 1 is half of 2, and 1/2 is half of 1, and 1/4 is half of 1/2. Okay? These numbers just go down by 1/2. If you go in this direction, or no, if you double 1/4, you get a half. If you double a half, you get 1. If you double 1, you get 2. If you double 2, you get 4, right? So if you have consecutive integers down here, every row, the value of y is going to double. Now, what's that say about the graph? And let me back up and say that, open math seems to think it's okay to just let people punch these numbers into a calculator without understanding them. Okay? Now, I understand that people are just making a compromise with the fact that nobody understands numbers when they come out of K through 12 schools. Okay? And it's a compromise they might feel is necessary, and I can't go there. Okay? I agree to disagree with them. It's a respectful disagreement, but you got to talk about it. Okay? I think it's important to know these calculations because they involve the rules of exponents that you have to know. And you really have to know the rules of exponents if you're going to manipulate exponential functions. So the idea that you can construct these graphs by punching in numbers in a calculator just seems to me really misguided. I can still respect misguided people, okay, if their heart's in the right place. Okay. Yeah, maybe it's me, it's misguided, I don't know. So anyhow, I'm going to do this graph. I'm going to write the x equals -2 line here. The x equals -1 line here. And get the chalk to behave. I'll write that. I'll write it in a minute. The x equals 1 line over here. And the x equals 2 line over here. And of course, the y-axis is the x equals 0 line. If you don't totally understand that, think about it until you do. Okay. Now we want to sketch these points on the graph, and we see that we have y values 1/4, 1/2, 1, 2, and 4. Now, if we start here and go to here and here and here and here, each of these numbers is half of the one before it. So I'm going to extend my y-axis a little. Then I'm going to put the y+4 line here. Now, people, when they start to make a graph, kind of automatically divide 10 units here and 10 units there and 10 units here, 10 units there. Okay. Or even worse, they're given a grid that's already marked off. Don't think you learn much about coordinate plane and the way the numbers behave in that way, although it's okay for introductions. Okay, so my point is now, I've got the y+4 line. I don't need a y+3 line to graph this, do I? I'm going to need a y+2 line. Where's a y+2 line? Well, here's y+4. 2 is half of 4. So y+2 is halfway to the x-axis from y+4. And then 1 is half of 2, we're gonna need a y equals 1 line. Which is halfway between 2 and 0, because of course the x-axis is the y equals 0 line. So we've got 4 up here. We've got 2, which is twice as close to 0 as 4. We've got 1, which is twice as close to 0 as 2. And now we've got to have 1/2 and 1/4. We've got to go twice as close to 0 here. And then we've got to go twice as close again to get 1/4. And I'm kind of out of room over here, so I'll label my y equals 1/4 line over on this side. Now it's easy to draw these points. You have the grid that allows you to draw the points without anything extraneous in the grid. So you have the point -2, 1/4. That's here. You have the point -1, 1/2. Well, that's here. You have the point 0, 1, which is here. You have the point 1, 2, which is here, and the point 2, 4, which is here. And these are the points that lie on the curve of the exponential function. Then we simply sketch a smooth curve. Goes through these points. It's kind of easy to do that if you do a good job of setting up your coordinate system. Okay. Now my class, as you know, if you're in it, we started with a 4x4 grid. Why? Well, because that's a logical way to construct this graph or the square graph. Okay. They both have to go out to 0.44 at 1.24. And you learn stuff by going from -2 to 2, and you get the whole picture of the graph. You can then develop into the whole picture of quadratic functions if it's a, or into the whole picture of exponential functions. So right there it is. Okay. Now I want to contrast this. Excuse me. I'd like you to make a table of y equals 3 to the x. Now, in the interest of time, well, don't bother writing out all the details, just write out the final result. Unless you aren't sure what the final result is, and then use the details. Okay, I'm not sure when the recording went off, when it went on, but just make sure. You got the table of y equals 2 to the x function. And here's how the table is constructed. We do it with the numbers. We don't punch it into a calculator. And we line off the graph. We need the x equals -2, -1, 0, 1, and 2 lines. Those are vertical lines here, 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 and here, and they're labeled. And we need lines for y equals 1/4, 1/2, 1, 2, and 4. We start at y equals 4. 2 is half of 4, so we come down twice as close to the y equals 0 line. The y equals 0 line, of course, is the x-axis. So we come down from the 4 to the 0 line, we go halfway, we get the y equals 2 line. Halfway there gives us the y equals 1 line. Halfway from that to the 0 gives us the 1/2 line. Halfway from that to 0 gives us y equals -1/4, the y equals 1/4 line. We plot the points in this graph, and here we have them. Okay, now we can do y equals 3 to the x. Okay, we make the table the same way using the same rules, and we get these values, and we say we're going to need a line for y equals 9. Well, I don't really have room to do it, but here's our y equals 9 line. and kind of smudge that. And then we're going to need a y=3 line. Well, we've already got y=4 and y=2 lines from the 2 to the x graph. If we didn't, we just divide from here to here into 3 equal parts, and there's where our y=3 line would be. But there it is, halfway between 2 and 4. And then y=1 and y=1/3. 1/3 is between 1/4 and 1/2, so there we have it. And y=1/9, which is a little less than half of 1/4, so it's going to be a little closer, a little more than twice as close to the y=0 line as the y=1/4 line. There it is. And we can sketch our points. These 2 points are lower than they are on the 2 to the x graph. And these 2 points are higher. And you can think about why that is. Pretty easy to understand if you think about the numbers. So there's our 2 to the x and our 3 to the x graph. Y=e to the x is a really important function. I've said it's kind of the function that's behind most of what we can tell about the mechanical universe. It's a big deal. Maybe the most important number in mathematics. It's approximately 2.71828. It's not hard to calculate that. But it's going to go in between. Since it's 2.7 raised to the x, it's between 2 to the x and 3 to the x. It's going to go in between these graphs, probably closer to the 3 to the x graph. And there we have it. So I also mentioned things like y=2 to the x plus 3 is just a graph of y. The graph of this is just a graph of y=2 to the x, shifted 3 units to the left because x has been replaced by x plus 3. And another little tidbit: 2 to the x plus 3 is 2 to the x times 2 to the third. You have to know the rules of exponents in order to do the exponential functions. So I advise people maybe take a quick look at the chapter on exponential functions. Start your brain working on it.